Hello everyone, we are explaining large-scale study of curiosity-driven learning. This is group 3. So our presentation delves into curiosity-driven behavior research, focusing on agents motivated by intrinsic rewards and predicting consequences of agent actions in diverse environments, such as video games, simulations, and navigation tasks. We explore factors influencing curiosity effectiveness and the challenge of predicting states in complex visual spaces. Our study suggests random network effectively model curiosity in reinforcement learning, but it highlights the value of learned features even in new game levels. We emphasize diverse environments, feature space, and curiosity limitations where agents self reward without progress. Next slide. Curiosity driven learning in AI entails training AI systems to explore and gain the knowledge driven by their inherent motivation to learn without dependence on external rewards or a set of objectives. Dynamic based curiosity learning is an AI technique where an agent explores its environment by rewarding itself based on the unpredictability of its own actions. This method encourages the agent to delve into uncharted territories, adapt to unfamiliar situations, and prove especially valuable for autonomous learning in scenarios with scarce or lacking external rewards. Here, the motivation behind this is we selected this paper since it discusses a way for AI to learn by being curious, which we find really interesting. It shows how AI can learn without needing specific rewards given by humans, which is a big deal in the field of artificial intelligence right now. The dynamic based curiosity learning encourages AI agents to explore environments by rewarding unpredictability, valuable for self guided learning in the absence of external rewards. It uses an exploration bonus to motivate agents based on embedding observations and predicting forward dynamics, resulting in higher unpredictability seeking behavior. Next page. Here, the effective feature spaces in curiosity driven dynamics are defined by specific characteristics. Efficiency is vital, with features being low dimensional and relevant to the observation space. The competence ensures that critical information is encompassed to prevent any missed rewards. Consistency is important to mitigate non stationary challenges. The non stationary rewards can affect reinforcement agents due to evolving forward dynamic models and the changing features based on curiosity. Next slide. The exploration delves into different feature spaces for curiosity driven learning. Here it is pixels, random features, VAE, and IDF. The pixels here are a straightforward approach which uses raw pixel data to train the forward dynamic models in observation space. The random features involves using an embedding network with fixed random initialization. These stable features can be compact but may not always suffice. The variational autoencoders aim to fit latent variable generative models and provide low dimensional features. They are approximately sufficient but can include irrelevant details and the features change during the training. The inverse dynamic features predict actions from the previous to the next states, and they also represent aspects under agent's control. It is easy to implement but may not capture the uncontrolled aspects. The stability of learned features varies, and each type has trade offs. Their effectiveness depends on the environment, and the stabilization may require some pre training VAE or IDF networks, but data access can be a little challenging. Next slide. Pooja, next slide. The key points in our approach for achieving stable and consistent learning across various environments are it's using the PPO algorithm with minimal hyperparameter tuning, normalizing the rewards by dividing them by standard deviation, and the standardizing advantages within the batches with a mean of 0 and a standard deviation of 1. The normalizing observations using randomly chosen agent run data, and also employing a large number of parallel actors 128 for enhanced stability. Implementing batch normalization to ensure consistent scaling of intrinsic rewards across the state space is also necessary. The done signal at the end of an episode can inadvertently disclose details about the reward function. Removing this done signal prevents bias towards simple solutions and maintains a challenging environment. In the infinite horizon context, death is merely viewed as a transition, to be avoided only when uninteresting. The agents naturally avoid death and prefer returning to familiar areas where they can predict dynamics. Overlooking this certainty can result in misleading experiments, especially in the scenarios lacking external rewards. And our assessment of feature learning methods across Atari games and Super Mario Bros. Reveals that curiosity driven agents achieve rewards without any external reinforcement. The mean reward curves illustrate this, showing how curiosity can motivate the learning. The raw pixel models and VAE features are less as effective than random and inverse dynamic features. Notably, inverse dynamic features outperform random ones in 55% of the Atari games. These results emphasize the value of curiosity based learning and the robustness of random features. This study provides insights into intrinsic motivation and its applications. The multi agent dynamics and RoboSchool. The RoboSchool juggling is where we examine agent behaviors and interactions in a customized environment using bouncing actions as a gauge for agent environment interaction. The RoboSchool Ant Robot, where we delve into curiosity driven learning within the ant ecosystem, focusing on spontaneous walk like behaviors arising from the agent's curiosity. And there comes the two-player Pong curiosity. Here we simulate curiosity among multiple agents and engage in a two-player Pong game. These agents independently learn and exhibit extended game rallies and intriguing behavior patterns. Here, let's look into the graph. The top graph demonstrates the impact of batch size on the performance of RF method in Mario without using any extrinsic rewards, whereas the middle graph shows the number of ball bounces in the juggling environment. And the bottom graph displays the mean episode length in a multiplayer Pong environment with a discontinuous jump indicating the emulator's limit. And the reward-free learning's advantage lies in its potential to generalize to unlabeled environments without specific reward functions. In this study, we pre-trained an agent with curiosity alone on Mario Bros. Level 1-1 and examined its adaptation to novel levels. Comparing the fine tuning on different testing levels to training from scratch, we found strong transfer in a scenario with matching global statistics. In the second scenario, with the color scheme shift, transfer was a bit weaker. Uh, Interestingly, we learned that these features based on inverse dynamics showed superior transfer, indicating that the curiosity driven learning equips agents for effectiveness exploration in different environments. Further, exploration across various settings is encouraged, and the experiment showcases agents' ability to learn valuable skills through curiosity, even without any external rewards. While dense rewards are effective in classic reinforcement learning, creating them is a complex task. Sparse reward experiments in 5 Atari games demonstrate that curiosity bonuses enhance performance in 4 out of 5 cases. These findings provide insight, although the idea balance of rewards remains a future research focus. Next slide. We've demonstrated that our agents trained exclusively with curiosity rewards can acquire valuable behaviors, such as playing numerous Atari games without any external reward, Mario navigating through over 11 levels without any rewards, the ant exhibiting walking like behavior, the Robo School showcasing juggling like actions, and the two-player Pong with curiosity driven agents creating game rallies. In general, these results indicate that in human designed environments, the extrinsic reward often aligns with the goal of seeking novelty. Game designers structure the gameplay to guide users, making the curiosity like objective a reasonable math for extrinsic rewards. Next slide. The supplementary findings demonstrate the potential of combining intrinsic and extrinsic rewards in Atari games with limited rewards. The figure here gives purely curiosity-driven exploration across 48 Atari games. The curiosity-driven agents demonstrate improved extrinsic returns. They outperform the random agents in the majority of environments, but also exhibit some cases where the agent's behavior appears close to random or even minimize the return instead of maximizing it. We offer an equivalent visualization showcasing the peak external achievements, similar to what's presented in the given figure. In the Mario scaling experiment, larger batches facilitate more effective exploration, leading to improved overall scores and the capacity to achieve comparable performance with fewer parameter tweaks. The comprehensive material here covers diverse topics from performance in different scenarios to curiosity driven learning. It is a valuable resource for educational report and presentation, offering a detailed information and statistics. The clear and concise presentation elucidates intrinsic concepts effectively. The content is comprehensive and the valuable for educational reports are presentations, but it may need condensing to fit time constraints. These limitations make it a bit hard to fit in. Additional context is required for a broader audience, and formatting efforts are needed to create visually appealing presentation slides. And coming to the conclusion, this study highlights the potential of curiosity driven learning by demonstrating how it can enable agents to investigate the environments without the need for outside incentives. It is excellent at providing thorough analysis, well structured content, and an ordered format. This paper highlights the revolutionary significance that intrinsic motivation plays in AI, indicating new directions for research and applications, even though several portions need further explanation and clarity. Thank you.